15.5 problem, which I will. 15.5, for example, one of the things that's covered is spherical coordinates. Coordinates, right? And so you're going to have some triple integral, right? dv, where it's f of x, y, and z. And what I'm telling you is, using that transformation that we just mentioned, we can rewrite the problem as a function of rho, phi, and theta, as long as we're willing to put what here? Well, you'd have to write rho squared sine phi, and then d rho d phi d theta. And someone might ask, why do you have to put this? And the answer is, that's the what? Jacobian. So that's what we computed. And about a week ago, I did some other examples of Jacobians as well. So I think, now that we're a little better with determinants, I think you should have enough that you can start tonight's homework on the change of variables kind of stuff. Okay? So, here I go, problem 75. Can I write this down? F of D is G big M little m. Oh yeah, I remember that from physics. Those are the two masses, right? I'm picturing two planets, Earth and Mars, or something like that. G is gravity? Oh no, G is the universal gravitational constant, yes? What's it equal? Thanks. And then we have some big fraction, and then d phi d theta. And so this is the magnitude of the gravitational force on a point mass, where the point mass m is a distance d from the center of a thin spherical shell of mass m. Oh, so maybe it's not a planet. Maybe it's a particle, like an electron, right? Maybe. I don't know. Anyways, we have d minus big R cosine phi, because I think they were nice about that. Why'd they do that? Because you're probably going to use little r in the problem somewhere. Sine of phi over big R squared plus d squared minus 2 times big R d cosine phi. Doesn't it seem like all these things are almost to the 3/2 power in the denominator? Okay. So there it is. We're going to use x is the cosine phi, that change of variables, and show that f of d really simplifies. That's the take-home message here. All right, let's try it. So part A. Use x equals cosine, let's get the angle right, cosine of what? Phi. And simplify. We're going to simplify this to a really nice fraction. No more integrals, not anything. All right. So you guys ready? Here we go. X is cosine phi. So that means we're used to say cosine phi there. I can write x. Isn't that nice? Here we go. So when we rewrite the integral, f of d equals, again, it's g big M little m over 4 pi. I'll fill in the limits in a minute. Let's see. We're going to have d minus rx. Right? Now the other thing that happens, I know about substitutions. Whenever you write x equals, you also compute dx. What does dx equal? Negative sine phi, more to write, d phi. Right? I try to make very certain that my Calc 1, Calc 2 students do that every time, so that Do we have that? Yeah, we kind of do, right, guys? Here's the sine phi d phi sitting. I guess I don't have a negative. All right. I'll throw a negative here. Is that okay? Now I have it. So now this is dx. And then we have d theta. Oh, but we need a denominator. So what's the denominator become now? It's capital R squared plus d squared. Those are constants, right? Minus 2 capital R capital D. Is that an x now? Oh, yeah. To the 3/2 power. Nice. Did this help? I claim it did. Matter of fact, so let's see if we can change some things. Theta is the last integral, right? The outermost. And it was ranging from what? 0 to 2 pi. I'm going to deal with that first, actually, in this problem, which is kind of interesting. And now the inner one, oh, wait a minute. That needs to be changed because it was 0 to pi. But now, since x of phi is the cosine of phi, you can compute things like x of 0 and x of pi, right? X of 0 is the cosine of 0, which is 1, and so this 0 becomes a 1. And x of pi is negative 1. Oh, see, that's what I could have done with that negative sign. I could have swapped the order of the integral. I think I'll do that. Okay, let me show you what I would do, honestly, next on this. I would take a look at this big, ugly mess. You see it? How many thetas do you see hanging around in that big, ugly mess? Nothing. And because of that, you could actually treat that as a constant, d theta. Whatever that integral is, I'm treating it as a constant when I integrate d theta. So what I'm actually going to do is I'm going to do the outside piece first. So I think this is a nice little trick that's not always shown. F of d is equal to, guys, let's write g big M little m over 4 pi. And remember that negative sign that I brought out? I told you guys what I'm going to do with that, right? I'm going to put it inside the bracket, and I'm just going to change this order of integration. So now that's a -1 and a +1, right? That takes care of that. Okay? So I still have, yeah, the big mess, dx. But what happens is, when you integrate d theta, you just get theta from 0 to 2 pi, right? So the 2 pi is what you get, and that cancels with the 4 pi, right? So far, I have f of d is equal to g big M little m over 2 times, now I have an integral to do. And the integral I have to do is from -1 to 1. Let me write it down. -1 to 1. What is it? It's d minus big Rx. I'll put the dx out here. Over stuff to the 3/2 power. What's the stuff? It's r squared plus d squared minus 2r dx. Okay. And there I am. And I guess I'm thinking of a substitution at this point, okay, where I let u be the entire bottom. That's my hunch.
It simplifies it.
I think that's the thing to do. We'll have to make sure we can account for everything.
Yeah, I definitely did not count for everything.
Okay, so let's try. Let's try. Let me zoom in a little bit too and really concentrate. Okay, so u is equal to the bottom. It's r squared plus d squared minus 2rdx. The only variable's there, right, guys? Okay, so then du is equal to negative 2rd and then the dx. Right? So I guess the numerator may be an issue. I mean, I have d minus rx. D is a constant. I could kind of forget about that maybe. Maybe what I'll do is this. Let's solve for dx. What does dx equal? I guess it's du over negative 2rd, right? So then I'll just kind of directly replace the dx with that. And then we still have the x in the numerator. Yeah, so just like I solved for dx in this equation, I'm going to take this equation and solve for x. How would that work? Well, I guess you would have x is equal to r squared plus d squared minus u. See, basically I would bring this term to the left, bring the u to the right. That's why it became minus u. And then I would have to divide everything by what? 2rd. So that's my hunch as to what the x is. Bless you. All right, let me carefully try to put everything in, see what happens. Okay, we get f of d is equal to g big M little m over 2 times, and here we go, the integral. Oh, I probably shouldn't go from negative 1 to 1 anymore, right? Because what do we have to put in? We put those values in for x, right? Bless you. So I guess if I throw in negative 1, I'm at r squared plus d squared plus 2rd, right? And if I throw in positive 1, I'm at r squared plus d squared minus 2rd. Guys okay with me on that? So let's throw some things in now. Well, the numerator is going to be d minus a big mess, is that right? Let's see, the numerator is going to be d minus, now it's r times this mess, right guys? Well, the r is going to cancel with that r. So it's minus, so why don't I make it plus and just reverse the numerator? Make it u minus r squared minus d squared. The r canceled with that r over, and then this is 2d, right? Or not 2d, that's the question. No, 2d. And then times, let's see. Well, the dx is becoming a du as long as I also throw in what? This negative 2rd, right? But negative 2rd is a constant. So we could throw that out front. And so now, instead of the denominator being 2, are you guys okay if I modify this and write negative 4rd? So that's the dx substitution. And then what do I have down here? I have u to the 3/2 power. Wow. Ugly. Are you with me so far? No. Show me where you got lost you. Alex? Resume. So I claim we are now here. F of D is equal to G big M little m over negative 4RD times the integral of what? I'm not going to write those limits again now. You know what, we could look back at them later. I'm going to write it as this. Du to the negative 3 halves, right? Is that the first piece? Is that okay?
Mm-mm.
No?
Can you put a parentheses around the %? I'll get mixed up with the other D's at the end.
Oh, yeah. That D is annoying. Yeah, that is no good. Yeah, let's put it as D times U to the negative 3 halves. Good point. Plus, now what about this mess? You know, I'm going to split this fraction up. So I have 1 over 2D times U to the negative 1/2, because there's U to the first and U to the 3 halves. And then I'm going to have minus, and I guess I have R squared plus D squared over 2D times U to the minus 3 halves. All that du. Yeah, I'm glad you mentioned that, Alex. That was a good idea. To be careful that the du doesn't look like a du. So now, we integrate. And we get what? Okay, we still have this fraction. GMM times negative 4RD. When we integrate, we get, well, this becomes U to the 1/2. No, U to the negative 1/2 times what? Times negative 2, right? Negative 2 U to the negative 1/2, right? Plus, now this becomes U to the 1/2. So we need to multiply by 2. So it's just 2 over 2D, or 1 over D, I guess, eventually.
No, consider D in the first one.
Yeah, what happened to the D in the first one? D in parentheses, so we don't get it mixed up again. I agree. Negative 2D, U to the negative 1/2, plus 2 over 2D, U to the 1/2. And now this is also going to become U to the negative 1/2. We have to put a 2 out front. So we have minus, and again, it's 2 times R squared plus D squared over 2D. So a lot of 2's are going to cancel. And what goes on the bar here? Well, those are the things that I didn't write down last time, right? So we have to put in R squared plus D squared minus 2RD. And then we also have to put in R squared plus D squared plus 2RD.
Let's factor those.
Oh, yeah. Good idea. Right? Let's factor that top one, because if you write the minus 2RD in the middle, you notice that a better way to write this is R minus D quantity squared. And a better way to write the bottom one would be what, guys? R plus D quantity squared. That's better. Especially because we have lots of square roots. This is really a nice problem. All right, so here we go. Good thing I have some extra space right here to kind of finish. I guess I'll work up here, huh? So I was down here, and I'm going to work up there. So this is, again, continued. What number was this? 75. Okay. So here we go. Number 75 continued. We get f of d is equal to, again, it's GMM over negative 4RD times a bunch of stuff. Actually, I'm thinking I want to factor out a negative. Do I dare do it now? Because I'm seeing a negative. Yeah, I'm seeing lots of stuff here, guys. All right, so let's factor out a negative. Let's get rid of that and make that positive so that that doesn't affect me anymore. And so I'm just going to write down what's in those brackets, but without the, I'm going to take a negative out. And I'm going to cancel the 2's also. So let me just be a little more cautious about it, and then we'll finish the problem on this other sheet. So we have, let's see, when I factor out the negative, I guess I have 2d times u to the negative 1/2. And then I have minus 1 over d times u to the 1/2. And then I have plus, well, this is r squared plus d squared over d, because those 2's canceled, times u to the negative 1/2. And again, we're evaluating that stuff from r minus d squared is up here, and r plus d squared is down here. That's really beautiful. So let's see what happens when I do various things here. I'm going to plug in r minus d squared into this mess. So I get g big M little m over 4rd times, when I throw in the r minus d squared, this is 2d over, now I'm taking the square root of that stuff, so it just becomes r minus d. Here I have minus, I'm taking the square root of this stuff, so it's just r minus d over d. And here, when I throw the r minus d squared in, it ends up on the bottom, so you have plus r squared plus d squared over d times r minus d. Okay. And now I'm going to subtract what I get when I plug in this limit, right? So I'm going to subtract gmm over 4rd times what I get when I plug in that piece. When I plug in that piece, I have 2d over, again, taking the square root, it would be r plus d. When I throw this in, I have, let's see, 1 over d. Okay, so it would be minus r plus d is what you get when you take the square root of u over d. And then we have, well, look what happens to this one. Do you see when you plug in the r plus d squared and you take the square root, you're just going to get r plus d. So this is going to be plus d times r plus d, and the numerator again is r squared plus d squared. Yeah? So I have stuff minus stuff. That's what usually happens. F of b minus f of a. Dr. Stitz told me Calc 1 is covering the fundamental theorem today, and we're using it. All right, so here we go. Can you combine these fractions? Sure you can. What's the common denominator for these, the first three? D times r minus d, right? So like this one here, we just want to multiply it by d over d. Make that a d squared and put a d here. Yeah? The other one we want to multiply by r minus d over r minus d, so let's just make this squared. That's beautiful. That's working out really nice. This is why physics people only work in variables. They want to see this happen. They get all giddy. You know? Engineers, they want the answer to the problem. But the physics professor, they just get all giddy when all this algebra happens. All right, so what happens here? Well, we have 2d squared again. Same idea. You guys with me? How many are with me pretty much right now? That's not a bad percentage. All right. So then here, Same idea, right? We're going to be multiplying by d times r plus d in the second piece, and so that's already there. So now the question is, do the good things really happen or not? Let's see. I know I have this equals g big M little m over 4rd. I know that. Times stuff. And what I'm thinking is maybe we can kind of write this as something over d times r minus d, and then we'll subtract something over d times r plus d, and then we'll see if there's anything else to do. You guys with me? All right, so let's see what happens here. Well, I get, in the first fraction, I guess I get 2d squared, right? And you guys know what this is. This is r squared minus 2rd plus d squared. But I'm subtracting it all. So I'm going to subtract r squared, and then I'm going to add r squared, right? That's gone. I'm going to subtract d squared, and I'm going to add d squared. That's gone. The only thing that's going to stick around is we're going to subtract negative, so it becomes plus, 2rd. I claim that's the first fraction. Do you get that? Wait a minute. Where did that d squared go? Cancel with that d squared. Where did that r squared go? Cancel with r. Well, sorry, wrong one. The only thing left here is the 2rd. And if you, who thinks they follow what I just said there? You guys with me? If you follow that, then similarly, down here, we're going to subtract, again, 2d squared. Same idea. The only thing that sticks around, I guess, would be a minus 2rd. Because all the other stuff drops out. That's really cool. Only thing is, though, guys, I shouldn't put that bracket there because we're going to need a common denominator to combine these fractions. What's the common denominator? D times r plus d times what?
D squared times r minus d times r plus d.
Well, we don't need the d squared. We could just stick with the d. But we do need to multiply this mess by r minus d over r minus d. And we do need to multiply this mess by r plus d over r plus d. Okay? And that will work. And I'm out of time. I will point out, though, it's really nice right now. If you factor out from this thing the 2 and a d, factor out 2d from this piece and that piece, this becomes r plus d quantity squared, and this becomes r minus d quantity squared. And you're there. I mean, what do we have to show it equals? There's going to be a little more canceling. The 2d's are going to cancel with the 4d's. And guys, I think you are here. Really. We're really close. But out of time today.